Hey, very good evening to all. I have Anish with me here, and welcome Madhu to this advanced Golang talk to concurrency. Yeah. So since it's just three of us, right? So we can actually we can do a small quick round of introductions. Okay, then I will start. Myself, Melvin Davis, and I work in a company called Sensible. I have been with Nexus. So what I'll give you introduction what Nexus is. So basically, Nexus is a tech community. It's just few of us as of now. So we are a tech enthusiasts who love to share about technology, learn new stuff, and grow all together as a community. That's what we do. So we have a bunch of workshops like this in Golang as well as in JavaScript. So that's it. So if you go to our meetup page, you can see all the workshops and tutorial, stuffs that we are trying to do. And so this is the second workshop of the series. That the first we had an intro series of Nexus introduction to Golang. So, have you guys were you guys present in that? Okay, okay, okay. So, so in the meetup page, I have provided the link to the video, but I'll just share the link here also. Give me a second. I'm sharing the link in the chat, and also the earlier workshops video is available in the meetup page along with the slides. And this is also being recorded, and we'll share the details of the video and the slides after the workshop. Okay. So next we have Anish. Can you go on? I think next Ayush, can you go? Hello, Ayush there. Okay, Madhu, can you? Yeah, cool. Yeah, cool, Madhu. I think Ayush want to introduce himself in through chat because there's some disturbance there. Ayush, go ahead. Cool, Ayush. Good to know. So we have Vikas also. Vikas, can you introduce about yourself? Yeah, cool, cool. Because I am also a pass out from NIT Calicut. Yeah, it's nice to see someone from same college. Cool. So without much delay, I think we can begin. Are you able to see my screen? Hello. Yeah. So you can ignore the background. Basically, I have moved to kitchen, so my parents are here. So they come from UK and have to do a quarantine. So I have moved to a different setup. So that's it. So sorry about that. And today we'll talk about concurrency in Golang. So when we say concurrency, there are different aspects to it. Like there are different use cases, and where this concurrency, understanding concurrency, actually helps solving a lot of problems. So when I first looked to it, first first of all, I felt that it was kind of multi-threaded environment, something similar. But concurrency is not same. Concurrency is like handling a lot of stuff together on real time. And there, like let me say a small example. Like if you have web server where like a bunch of requests come and a lot of activities do go on, like DB writes might be going on, and you might be getting some data from Redis and stuff like that. So these things are coming under concurrency. So when you write application, especially the web applications is all, you might need this concurrency to work in your way. Okay, cool. So today what we'll do is we'll go for a small intro, then we'll go into concurrency and much deeper into CSP. So CSP is communication sequential processes. So that how we are communicating in Go using concurrency and all. And then multi-threaded programming. Actually, it's not accurate to say multi-threaded programming because it's happening under the hood. Like Golang takes care of the spawning threads and all. So those things are happening under the hood, and as a developer, I need not worry about this. That's the best thing about Go. In other languages, you have to manage a pool, and you might be using some libraries, and you have to optimize a lot so that you don't overuse your system's CPU and all, and also to make to utilize the number of cores available and stuff. But in Go, you don't have to worry about all those things. Go just takes care of it, and it has got a beautiful scheduler and stuff for that. And I'm hoping if we have enough time, we would end with a demo. And since just few of us, when you have any doubts, like when we pass one topic to another, if you have any doubts, do feel free to ask to me. Okay. And we have also Anish here, in case he also can pitch in and help you guys with that. Cool. So let's start with concurrent. So in the last talk, we talked about writing functions, and here I have something similar. I have a main function, and then I run a function called when will I run. So basically, when will I run, what it does is it says I'm going to run, then it pauses for a second, then I say I complete it. Then it completes the next one. I know when will I run. So that's the next function. So I just run this. There is nothing there is no kind of complex kind of thing. It's just plain simple. If you have any experience with any kind of programming language, you would definitely understand what this code means. I mean, it's just running all the code sequentially. Then what if I add a Go in front of it? This is how you write concurrent code in Go. If you want any function to execute concurrently, you write Go in front of it. In Go, it's called Go routines. So to turn any function into a Go routine, you just need to give the keyword Go in front of your function. That's the beauty of Go. Like that's it. There's no more spawning threads and stuff like that. It's very simple. Now, when I run this, what will happen is, I thought I would only I know when will I run. That only that function got executed. The other function didn't get executed. So what essentially happened is, when I ran this function, when will I run? As a Go routine, it got scheduled, and Go runtime, it doesn't wait for this function to return or complete. It will directly go to the next function execution, next line, and it executed the function, and scheduler decide when to run the function, the Go routine that we spawned. Now you can see since the main function exited right after executing, I know when will I run. What happened was the other function didn't get time to execute. So wanting to keep in your mind that if you're spawning a Go routine and the runtime itself get exited, if the main function exits, then your Go routine, everything goes blank. It get executed. It won't get executed. So as such, this function is not of no use. Then we'll just see how we can actually make use of it. So what I did was, it was the same program. It's just I added a 2-second delay before executing this function. Okay. So when I run this, you can see that I thought I would run after you. I know when will I run. That function again got executed, and it waited for 2 seconds. Meanwhile, the Go routine that we spawned, it started running. It started first told I'm going to run, then it waited for 1 second, then it said I completed. So this is how we can do this. So in a Go concurrent environment, we can execute functions which are not running in sequentially. I can give a really good use case. Suppose you have a web server, and when a request comes, you can't actually say at what time that the web request will come. It may come at some point, and for example, if you are having a CRUD operations, and there might be a chance that one web request comes to write an object to your database, and you are facilitating that request. All of a sudden, another request came to read it. So if the DB transaction is not complete, there is no point. showing it. So, but you are not in control. In a web server, a lot of requests comes and you are not in control. That's a perfect example for a concurrent environment. So let's take a step back and see what concurrency is. Concurrency is dealing with lot of things at once. Parallelism is about doing lot of stuff at once. So you can with Go you can still write parallel programs. To write a parallel program, the thing is that you have to make sure your program executes in multi-core environment. I means you have the if you have availability of multi-core in your CPU, then you can definitely run the program parallelly. And there are ways to control those. Like if you want your program to run on single core, or if you want to run it on multi-core, you can actually control that. Go has given a lot of tools and a bunch of tools to do that. So we'll see that in later. And this concurrency feature, it might seem that this concurrency feature is new, but actually it is not that new. A bunch of languages has actually implemented this feature way long before. Like Erlang has one of the closest implementation to the initial paper that Horace has written. So there was a paper written there in 1978, and also by Dixas Girder commands, that's in 1975. So Go has taken inspirations from this. So what is a Go routine? Like we understood what a concurrent environment is. It's something similar to our web request or web server, and we spawn Go routines to cater that. Now, what is a Go routine and how is it different from an OS thread? So first of all, it's not a thread. It's a very lightweight green thread, and there is a concept of coroutines. So it's something similar to that, where it is not. It is so usually OS threads are managed at the system level, but Go routines are managed at the Go runtime itself. Go scheduler manages it. So what it seems that for an OS, it seems Go scheduler is taking care of one thread. It's using one thread or multiple thread as required, and it's keeping in touch there. So there won't be multiple context switch and stuff like that, which actually degrades the performance. That's why Go performs a lot well in comparison with other languages when dealing with web applications and all. And there might be only one thread in the program, and as I told, Go scheduler takes care of. You might be spawning up hundreds of Go routines, but regardless of that, there might be just one OS thread underneath, and you don't have to worry about it. If the Go needs to have multiple OS threads, then it will definitely spawn that, and you can also control those things. And so and there is a really beautiful article about Go concurrency by Ardan Labs. There is a link to this. I'll share the links there. And there it explains how the Go scheduler works. That's a bit advanced topic, so I won't be discussing that in this talk. So in Go, how we are doing the concurrency. So okay, yeah. Ayush asked question. Yes. Control threads. Does this? No. So what Ayush was asking was that we are unable to control the threads. Does this create any problem? Definitely not. It doesn't create any problem. So like when I have to manage the threads, and I have to make sure the thread pool is alive and it's not exhausted. If it is exhausted, then I have to schedule it. But for Go, it doesn't matter. Like if I have hundreds of Go routines spawned and there aren't enough threads available, then Go will take care of it. It will take care of queuing it or scheduling those kind of things and prioritizing the functions. Those things Go will take care of it. So it won't necessarily create a problem, but there are instances where you shouldn't do Go like Go routines for this purpose. For example, if you have heavy computation involved, Go might not be the right choice for you. Like if you are spawning up a lot of Go routines and trying to do a lot of computations, it might not actually work. So you might need to do something else. You might have to choose a different language or library altogether. Does that answer my question? Cool. Yeah. So how Go does this? So Go has two methodology of doing it. Like one is the conventional lock mechanism where if you're familiar with other programming language, you will have one lock. You can, when you're accessing a variable or global variable or shared memory, you can use lock to specify that no other objects reads to it or writes to it, or read or write locks can be applied to it. And once you are done with the memory or the variable, you can release the lock. Only then others will be able to access the variable. So that's the one way. Another way is sequentially communicating this. So what is this? So basically what it means is you have a couple of channels and some methodology to synchronize your communications with the functions between the Go routines. So how we are going to do? So I'll give you a small example. So like I have an suppose I have a cache kind of mechanism where you can think something similar to Redis. I have a cache and I have to get some data from that, and I at the same time I also writing data to it. So I can use channels to request the cache to give me this particular data, and also I can use the same channels to communicate the data output from the cache. So what channels are? Channels are like a you can think of it like a small pipeline, and the pipeline has two ends. So there is a receiver end and there is an sending end. So this is how you do it. You can declare a channel like this, like you can do a make chan int, and and this is how you send the values to a channel. So it's like there is an this is the operator that we use to send a value to channel. And you can see here when I define the channel, I told us channel of int. It means this channel is making sure integer values are passed from the sending end to the receiver end. And this is how you receive value from the channel. Like you say value or name of the variable equal to this arrow function and the name of the channel. So suppose if you are not assigning any values that coming out of the channel, you can actually ignore this. You can just type it like arrow operator, then C. That will also do the channels. And there are unbuffered channels and buffered channels. So buffered channels are like, it has got a capacity. Like in real world, you can think about it like a pipe of length 10 centimeter, and you can put some small paper balls into it, and since it's just 10 centimeter in length, the number of paper balls that can put into it is very much limited. So that's like three if I make some 3 centimeter kind of paper boards, I can put 3 of them in. Similar to that, if it is a buffered channel, I can put 3 items to this channel at a time. And if I have to put more items, basically I have to wait till one of the item get cleared from the channel. That means if there is any listener listening to this channel and it is getting moving one of the item from the channel, only then I can push another item into this channel. Channel is something similar to a queue. So we're first in first out kind of mechanism. And there is one thing called unbuffered channel. So unbuffered channels are channels with zero capacity. There is no capacity. If you want to push something to it, there should be like there should be a receiver there. If nobody is listening to it, your pushing will be waiting. Like the sender will have to wait till somebody is there to listen to it. Then comes so while using Go channels, most of the time people run into this small kind of issue, especially for the first time. I have often run into this program. This is an issue. This is a deadlock. So what deadlock is, suppose I am trying to push something to this channel. So I initialize a channel and I'm trying to push something to this channel, and there is no one to listen to it. So these kind of behaviors actually can get into deadlock, where basically I'm trying to push something to it, and only after pushing something to that channel I can go to next line. Okay, but you can see there is no one. If I haven't made any Go routines or anyone who listens to this channel, basically I am just deadlocked. Like the execution won't go to the next line until somebody listens to this channel, and if I haven't spawned any go routines to listen to this channel, that means effectively the program is not going to go anywhere. So if I have deadlocks, immediately Go suspends the program. So a error is thrown down. And okay, so if you have guys, do you have any doubt? uh, I think I'm not sure that I went too fast. Yeah, okay, cool, cool, cool. So we'll delve into few of the patterns, like how one of the ways we can actually implement CSP in Go. That means what's the idiomatic way to write Go concurrency code. And these slides, I have taken these slides from one of the oldest talk from Rob Pike. So and till these days, these methods holds a value. So I do remember, like one of the developer that who came into our last my current company, he was working on one of the critical piece of code, and there he actually didn't follow the methodologies that Go says, like what are the idiomatic Go code, how we should communicate data to here and there. So and it actually created a lot of trouble there. What happened was, instead of communicating things in the way of that the ways that the patterns that I'm going to discuss, instead of that it was done in a much different methodology, and in the end we had to spend a lot of time to figure out what's happening, and it's very hard to decode the issues. Okay, so here is it. So I have two structures. One is a resource structure. Basically, there is a URL and there is a boolean to denote whether what we are doing, like whether we are polling or not, and what's the last time when we polled the resource. And there is one resources structure where data is an resource, list of resource, and there is a lock to denote whether this structure is used or not. And in the typical manner, if I'm trying to do in a typical manner, this is how it looks. The code would look like I will be trying to range over the data, and if any of the data is in a polling section, then I would continue it, like I will go to the next set of data, and if the data is not polled, then I will do similarly. And if I'm found that okay, data it's not polling, then I'll do the lock and so basically you can see the lock and unlock to free the resources here, and after that have to update the polling and last poll part. This is how normally I would do, like an polling activity in a normal scenario without the Go idiomatic way. But if you do it in Go, this is how it actually look like. You will have an in and out channel, and you, as usual, you range over that channel. So basically you can actually, if you do this range kind of thing, you can actually get values out of the channel. And this is it. This is how you will do it. Like you just get the data from the channel and you just send it out to this. So this is a way Go, like if you do the code in a Go idiomatic way, the advantage is the code will be more readable in comparison with other method. I'm not saying other method is inefficient or it won't give performance. It will give all things that you want. It's just that code readability, at a code readability standpoint, it would be much better to write in this method. Okay. So these are the different patterns. One is the generator function. So what generator function is, like I define a function and it returns a channel, and from that channel I can publish the values to which some of the listeners might be listening to. For example, I have this function called boring. What it does, if I give a message string to it, it would do it will actually print the message as well as the iteration number, and it sleeps for some time, then publish the next message. Okay, so if I, and you can see this function is being called here, it's initialized into C. sees a channel. So this is an read-only channel, and what it does is it prints for some time, then it exits the program. So if I run this, basically I initialize the function message with boring, and it says you say the text that we passed, then it printed 1 2 3 4 because we iterated over this for loop. Then it said it exited the program. So do you guys have any doubt on this, like how it ran? Then another way to use this is as use the channels as handlers. So suppose I have multiple people, like here in this case, the boring function that we saw earlier, this is the boring function. Here I initialize multiple boring functions and I got multiple channels. So I am trying to print values from each channel altogether. So first I initialize this, then I am printing the value from the Joe, then I am trying to print it from Anne, then I do a iteration, then come back here, again print the value from Joe, again print the value from Anne. That's what it does. So basically it's kind of clubbing the all output together. So this is a way to get values from service. So suppose I have a service which listens for updates from other services. For example, suppose I have a notification service and I send notification out. So how notification services works is that you send the notification to the client, and after some time you might get the delivery report that this message was sent to him. Or you can see, take an example of WhatsApp. You send a message to WhatsApp, you can see the 2 ticks and 2 blue ticks denoting that one, it is read by the customer in the end, or whether the message is delivered to him, those kind of things. So if you are using a notification service, then you send the notifications and you need the updates from the notification, the post back updates from them. So you can listen, suppose you have a listening service, so you can think something like similar to this. And there are 2 channels, like suppose you have WhatsApp messages as well as the push notifications, mobile push notifications. So I have to I can get the values from both of these services in this similar manner. Like basically I initialize the functions, the listener functions, and I'll be waiting for the instead of this for loop, I'll put it as an infinite for loop, and I'll keep waiting for the responses from the or updates from the services, and I can keep logging it or whatever activities that I want to do. So this is another way of using the channels. If I run it, you can see Joe executed 0 0, then Anne executed 0 1 1. So basically you might have, I'll just run it again, you might see some kind of delay in between which is not uniform. Basically the Anne's this particular line get executed only after Joe get executed, and after Anne executes only then it goes to this. So basically receiving a value or pushing a value, sending a value to a channel is a blocking activity. So while implementing these things in your code, make sure you have enough timeout and stuff, to which we'll come later. So another way is multiplexing. So here you saw that I was waiting for all of this to work. So there is an issue here. Unless Joe gives some value, Anne can't get value from the Anne service. Okay, but what if Joe gives a better mechanism, like Joe gives output much faster than the Anne. For example, again we can take the example of the WhatsApp thing. So WhatsApp messages has a limitation that you can send only the bandwidth that with which you can send the notification to WhatsApp is like 20 messages per second, and maybe push notification has like 1000 messages per second. So push notifications goes much faster than WhatsApp. But if I do in this way, the problem is that I'm actually have to wait for one WhatsApp message update to come before logging in other updates. So basically I will be holding up a lot of stuff in the memory, eventually pumping up the memory usage in the application. So is there a better mechanism to do this? There is a fan-in mechanism. It's like Whenever one channel gives one output, just process it rather than waiting for the other. So this is a way to do the fanning in. Like if I define a function and I take two inputs, like I take the input of all the channels. In a better mechanism, you can actually get the list of channels from which you can actually get the channel values, and like that you can basically what it does is whenever it's getting a value, basically these two are doing a join, clubbing the values and putting into the channel. So whenever they receive any values, it's just putting into this output channel. Basically we are returning this output channel C, and whenever any of the values come from the input channels, it's just putting into the output channel. So if somebody is waiting at the end of C, here, if somebody is waiting here, it will get the values regardless of it won't be slowed down by single service. Like if I have bunch of services, if suppose as in the last example, if WhatsApp service is giving me delays, it won't affect logging the data from the push notification service. Yeah, you can see here it was much more dynamic. Like basically we saw a delay after the second Joe message. We saw a small delay. That was because both of them were taking time. But you can see Joe publishing multiple times here, while Anne was not publishing. This was happening because whenever the values came through the Joe, it directly got passed to this channel C using this fan-in. So this is a one way of doing this. And there's one more way of doing this, that's using select. I will discuss that later. And so up to this point, are you guys clear? Yeah, sure. This one. Yeah, yeah. Okay. So I'll just, so basically this is not two operator. Basically it is trying to get a value from this channel. Input is again a channel which gives string values. Okay, and it is pushing the value that coming from this input channel to this channel C. So one way to rewrite this, I just grab an editor. Are you guys able to see my screen? Okay. Okay. So if I am going to modify this as a small bit, I think it will be much more clear. So effectively, this is what I wrote. In the earlier example, I was putting that input from directly to C. Instead of I am putting it into a variable and assigning this variable to C channel. So does that, so the other statement, the second statement is essentially translating to this. Does that solve? Yeah. Cool. Anyone else? Okay. Yeah. Then we'll go to the other one. So basically, like send a channel on another channel. So this is a kind of mechanism that we can be used to like, so here we saw this thing, right? Like basically I was fanning in multiple channels, so I have to accept the number of channels that are coming through. So suppose what if this is a dynamic list? Like I can only accept a fixed number of things, but what if the number of sources who are going to give the inputs to this fanning system itself is dynamic? So in these kind of scenarios, actually I can make use of sending channels through another channel. So I can wait for those channels to come, and if the new channel comes, I can spawn a go routine to do this. And just make sure when you are ending the function, make sure you write a close function to in the differ to end that close that channel. Okay, so yeah, so here what it does is here we are using a wait kind of channel to send the messages. Yeah, so here in this case, here is an example. What we will do is we have a for loop, and I am sending, I am receiving a message from this particular channel, and I am printing it. Then again, getting the second message, then printing it. Then it sends wait message to it. So basically, this enables sending values to it. So essentially it means to wait for some time before sending out the message. So you can see that, like basically it was printing, or like in the unlike the earlier examples, you can see John and got was printing all together, and here you can see that when it receives a wait for it. So basically I was sending the wait command, and whenever it receives a wait, it actually was waiting for a random time. Then basically go for it. Oh, was I enough clear on this? Or? Okay, so basically, suppose I want to keep the order, like if I get some message. So the one problem with concurrency is that you are not able to identify at what order things came out, requests came in, what's the order, and in concurrent memory it's very hard to track, right? So what if you can set a wait channel to get this order, like to restore the order with which these things happened, like the order with which like the initial request came, and you can, if you want to preserve that order, there is a mechanism to do this. So this is the pattern of doing that. So suppose you have message as a structure, and there is a string inside that, and there is a wait channel. Okay, so wait channel is a channel of boolean. Okay, so the way I would initialize this is I say message, and this is the message that I wanted to print, and then I initialize with the wait for it. Wait for it is a channel. That is an basically this is a channel of boolean channel, and what I did was I was doing a wait for. I send a signal to it. Okay, so you can see what's happening here is when I send a signal to this wait, this true value to it, unless somebody is there to listen for that particular wait, it won't run. If I go to the earlier example of unbuffered channels, I told here that for an unbuffered channel, for that to work, like for you to push some send a item to this channel or receive from it, both and needs to be there. Like there has to be a sender and there has to be a receiver. If there is no receiver or if there is no sender, the other party would be basically blocking it. So similarly, this thing like if I want to push something to message 1, it can only be done if somebody is listening to this message, like somebody listening to this channel. So here wait for it was the channel that was initialized here. Only after this particular wait for it, it will actually be able to run this. So I actually one thing I will do, I will just show the source code. It will be much more easy. Oh, sorry. Start the program. One second. I'm sorry, I'm not able to find that particular. Can't. Yeah, yeah, I'm not. Yeah, I think it's. So this was the program. So as usual, this is the boring function that we wrote. So what we effectively doing was, we were in this boring function, we were making a channel as usual, and we are sending out values to that channel, that string channel, and it was done in this manner. I think okay. I'll just come back to it in the later period. So okay, I'll just come back to it later. I am not able to find another example for this. Okay. We move to the select pattern. So if you know what select is, like there is a something called switch case in Go, which is very similar to, like it's similar to all the other programming languages. Much similar to that, there is something called select, which is used in Go for the concurrent environments. Basically, to deal with the channels and all, you have something called select. So in the other example that we showed here, where first we were trying to print everything using a like dump for loop, then we were trying to fan in everything using these functions, and still this function still doesn't look that good, right? Like it still looks a bit ugly here. You have a bunch of for and functions written like this. So there's a better way to write this code, that's using the select pattern. So what you would be doing is, you write a select here, and then you say case. In the case, you can actually take a value from one channel and another channel, and all the channels that you want to multiplex in, and you can get the values from here. Okay. So so if some any of the channels comes in, then it shows the value, or pass it along, or how you want to deal with the value, you can do this. So this is a way to do it. So if you want to infinitely listen to a bunch of like a bunch of uh, channels, the way to do is put this select inside a for loop. Okay. So this is a way to do it. Like in the earlier fan-in mechanism that we discussed, this is how we are going to do it. So we just push these things to the channel, but we'll use the yeah. So yeah, this was the difference. We just put the values in here, and then we will use the select to get the values out of these inputs. So if something comes from the channel 1, then pass it along, and if something comes from channel 2, then pass it along. And if I run this, it works exactly a similar way that we ran the earlier fan-in function. The only difference was that instead of using multiple go routines to fan in all the values, we are just using one select, and inside the select we are using all the inputs from those channels. And next problem is, suppose like when I send a web request, another issue that happens is sometimes the remote server might hung up on me. Like, so if you are writing a software, you have to specify what's the response time that your web server would give. It might be the error response or it might be success response, but you have to give your response in a specific time, because that's very much important in making a lot of critical decisions. Like for example, if I am making a search engine, and if I am searching some values for something, and I have a bunch of services like the data from the old web pages, or data from the news feed, or data from the sports section, or data from the some video service. So if I have to make something similar, all this service has to return the data in time. Suppose I search something, and one of the service, maybe the video streaming service, didn't return me data in time. That necessarily doesn't mean that I have to make the whole service wait for it. I have to say, okay, video service didn't give me data. I have to say, okay, that's a timeout. I have to get out of this. So that's the reason we need to add timeouts. And this is a nice way to do the timeouts. Like, suppose this boring function didn't return something, I can use a timeout. Or suppose this boring function is keep on sending things, but I want to listen for only 1 second. So this is so basically this time dot after, this is a function from the time module, and what it essentially does is it will send a value after 1 second. So this is a library function. So if I run this, what it will do is Joe will keep on printing stuff, but after 1 second we will say you were too slow, and we just do a timeout. And a lot of actions do need this timeout thing. So yeah, yeah, sure. Mm. Yeah, 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 yeah. So so what I mean is that there are two switch cases, and like, I mean, sorry, there are two things running in the background. Like this timer is running in a different go routine. If you want, we can actually go to this definition of this. Uh, So effectively it will be running in the background. This timer will be running in the background and counting the stuff. And once it's done counting, it just pushes to this channel, and in the in this select, it effectively gets this channel when some value comes to this channel, and if nothing is blocking anything, it will actually get this value and execute this. So if I want to go here in this function. Hmm. Yeah, this is the function, And if I go to its definition, yeah, this is a beautiful thing about Go. If you need to find the implementation how it's done, you can actually go to this particular like source code and see. So what it was doing was it was actually giving a new timer uh, and its channel. I'm not sure if I can find the new timer here. Yeah. So this is in time. This is how a timer codes look like. I just increase the size of the screen. Yeah. So there was a timer and there is a channel that we initialized, and where there was the like we started running this timer, and once this is run, it will return that. Yeah, it was returning the timer and it was actually starting the timer. So I'm expecting this to be a concurrent stuff. Yeah, I think this is some. Yeah, I think this is an implementation. Like, yeah, we have to hunt for that function to get it. But idea, yeah, it means if you are doing something in the select case, the other go routines or stuffs that happening in the background keep on happening, and you will get the value in your go routine in the select. And Go scheduler works in a different way. Like it actually manages to run this task background in the background, and the earlier the earlier link that I mentioned about the Ardan Labs, it actually explains how well the scheduler runs these things in the background. How it is scheduling when to run a Go routine and when to not to run a Go routine. And sometimes some Go routines might be taking too much time to run. In that scenario, pause that Go routine for some time and give the time for another function or Go routine to run. Those things are done by the scheduler. Does that explain? Yeah. Yeah. This one or okay. Yeah, this is the one, right? Okay. Mm. Yeah. Oh. Mm. Okay. So, so here, okay, the scenarios are like if some value comes, suppose C1 is somebody is pushing values to C1 and somebody is pushing values to C2. Okay, and in those scenarios, it will actually waiting for C1 and C2 to value to get resolved. Like somebody is getting some receiving some values from this channel, but you can, as you can see that like this 23 is actually pushed to C3 altogether. Like, and here suppose if nobody, and suppose this C3 is an unbuffered channel, okay, and nobody is listening to that, in that scenario this will also get blocked, right? uh, yeah, so if any one of them get executed, in those case, it will like the one that get executing in the first place will take place. And the reason we are adding a default clause is that like suppose nobody is listening to these channels, like nobody is listening to C1 or sorry nobody is writing to C1 or C2 and nobody is listening to C3. In this case you are actually like going nowhere. So in for this scenario you have to put a default. And default, the problem with default is in a concurrent environment we are not sure like when somebody will push to C1 or C2, or if somebody will listen to the guy who is listening to C3 is free or not, right? So the problem with this statement is it will directly go to execute default if all the other channels are blocked. So that's why if you add a timeout to this instead of this default, if you add a timeout, if you add a timeout to this, at least you get the breathing space to wait for the other channels or something to happen, and after that you say okay, nothing is working, I'll just get out of this mess. So for example, if you're taking the earlier example of that search, and suppose none of the this was suppose C1 was the search like the news service, and C2 was the video service, and C3 was some kind of meta logging that we are doing, and we are not able to log the information, or we are not able to get the data from the news service or video service, then I would say I will wait for this service to happen for some time. It's not happening, then I say okay, there's no point in making the customer wait for my results to come. Let the customer show whatever results that I have. Those kind of things can be done with the timeout. Yeah. No, not exactly. No, somebody has to start this. Like somebody has to manage this channel. Somebody has to push values to this channel. Go won't internally do it, but I mean, somebody does it. Go will manage those channels, those Go routines. And yeah, I think this was the example that we were like just talking now. Like instead of using default, if I use a timeout thing, it will work better. Uh, like so in the select statement, the one that was discussing just now with the doubt that what should I do, like how the default thing work, and what's a better mechanism to use than the default. So that's what this is. And yeah, so this is another way to do quitting. So suppose I have a program, suppose I have a service, and something similar to, are you guys familiar with the EC2 services? Like we have in the AWS EC2, you have a lot of containers running, and suppose there is a service running and you want to stop that service. For example, there might be a login service going on, and you might have some issue over there, and you don't want any more authentication to happen, and you want to shut down that service. Then you send a stop signal to this service, and suppose when you're sending a stop signal, this service might have a lot of things happening in the background. Like it might be listening to the DB, or it might have some unfinished business with writing some transaction, or maybe booking some ticket in another service and stuff like that. So if you are sending a quit signal to the service, what it can do is it can do the cleanup action, like stop all the DB interactions and stop sending the other service, like the tickets to other service and stuff. You can stop all those things and gracefully shut down. So for that you can use this kind of mechanism, like the quit mechanism. So basically a quit was a channel again of Boolean type, and this boring thing was running. What I did was it was running for some time, and I send the true signal to quit. It means, and if somebody is listening, like in this select, it was listening to this quit channel, and as when I'm sending some values to this channel, basically I was printing. So basically I was sending some values to this channel, and it was printing them. And after some time, after it got printed, then you can see there is no one to listen to this channel, and at this point select is blocked here because there is no one to listen to this channel. And after this random for loop, it sends a true signal to quit. Now this select doesn't need to wait for anybody, it can just quit because the signal came through the quit channel. So this is a way to gracefully exit your out of your applications. If I run this, yeah, after so the random number was 10, like here the random number was 2, and it run for 2 times, then it sent the quit, then it exited gracefully. So if I want to see this program, second, so yeah, I do in this program, after this quit, if I say something like quit. So basically I was trying to do some cleanup action. So if I run, just refresh this and run this, it doesn't quit here. So yeah, this is what I so the cleanup thing was having that, and you can actually proactively give a quit signal, like return something in return to it. So for example, when the service quits, again the case of the AWS stuff, I was actually sending some values to it and it got quit. Now AWS has to restart the service, like it has to show the user the service has stopped. Now you can do whatever you want or start a new service. For that, it has to know the existing service has exited. So this is a better this is a mechanism where you did the quit, you cleaned up whatever things that you want to do, and you are acknowledging it. You are acknowledging that you have quit it, and you are sending the acknowledgement signal here. So like there's a quit signal. I started the boring function, and I like keep on printing some of the values. Then I send by signal to this function. Then the function exited, and we got the acknowledgement here. So if I run this, we ran for a random number of stuff, and Joe says see you. So basically it also it exited. At the same time it sent an acknowledgement. So these are the different mechanisms with which we can actually run the, like these are different patterns with which I can actually implement concurrency in Go. So you have any doubt in this, like any of this? Anything? Okay, okay. Before going further, I will just go through one example. The one that we got delayed. So the one. So just okay. Basically, in the other example where we didn't get in this particular, I was not able to pull it back then. So this is the one. So basically, we were doing that wait thing, and so this is how a boring function is defined. Here I have an iterator, and this iteration I get a basically I push a value to this particular channel, and then wait for some time, then wait for that thing to acknowledge, basically the wait signal to come in. So here what was happening was I got this message from this C channel and printed them. Then only after making sure the second thing is printed, I was sending the wait signal to the this particular channel. So this will send, like this particular function will send another set of data only after getting the wait wait for it signal. If it doesn't get the wait for it signal, then it won't send a value, like it won't send the next value. So this was a mechanism to synchronize between like multiple sources. If there are multiple sources of data, you can actually synchronize the values, like printing those values, or wait for some of the values get printed in this way. Okay. Then so next I'm going to how to do the multi-threaded programming, and it's fairly simple. As you know, Go has one scheduler which takes care of this Go routines. Like if you spawn multiple Go routines, Go schedule takes care of it. It will decide when to run this Go routine, when not to execute this Go routine and stuff like that. And if some Go routine is taking too much time, park for it sometime. Those things are decided by Go scheduler, and underneath it it utilizes different threads to keep this Go routines up and running. If it needs more threads to keep the Go, like suppose I have like 1 lakh of Go routines to run, and if it needs more than one Go routine, sorry, thread to run these things, it will keep on increasing number of the threads as required. So there is something called max pros. So what it does is, by default Go runs with number of cores. If I have 4 cores, it will use 4 OS threads to run this, like to multiplex, like to run this all Go routines over it. And earlier it used to be 1, like it was a time when Go was initially developed, it was using 1 as the default value. But now like if I run this thing, for example, sorry. Yeah, so yeah, so here so this is a there's a library called runtime, which is a standard library. In this standard library, yeah, so in this standard library, if there is a function called go max procs. In this function, you can actually programmatically set how many number of threads that you want to run. Okay, and but if you have 4 cores, and if you are setting 8 as a max number, it might not play well, because at the end you will be keeping some of there will be lot more context switch between the threads, and eventually your program will be slower than expected. And you can also get the number of CPUs available to understand the default value. For in this case, um, this is the function I was trying to get number of CPU in my system that's I'm running, and print the number of cores. So if I'm running this, it's saying number of cores is 4. Basically, in my system there are 4 cores. So with this API, I can actually get the number of CPU available, and take advantage of that, and keep my program processed in a multi-processing environment. So that is writing a multi-thread programming goes much simpler. Like you don't have to worry about it. You just try to go routines and handle it in the right way, in the idiomatic Go way, and rest of the things are taken care. And if you still want to play ahead with it, there are a bunch of stuff that you can do. So in this particular runtime is the library. In this library, there are a bunch of operations. Like there are go max procs, where you can set number of OS processes, and there is a Go shed. Basically, you can play around with the Go scheduler to go ahead, and you can get number of Go routines that are running and number of CPU cores. Those kind of things you can actually set those things, and in different kind of monitoring systems. Like if you are building some kind of monitoring platform, or if you have some of service that you need to monitor, these is the library that you want to check out, where you get differently the idea about the health, and like what's the number of resources used and how healthy is your service. Those kind of information can be get there. Yeah, so here's asking, can you share? Yes, definitely. So I'll share the PPT in that meetup page, and I'll definitely share that. Okay. In fact, I can do right, like once after end of this talk, I'll share it. And so you guys have any doubt altogether? So yeah, yeah. So we have no. So we are at the end of this talk. So what I have is the link to these things. Anish, do you have anything to add to this? Okay. Okay. Mm, should we write a small program to uh, to demo it? Okay. Yeah. Oh. Okay. Sure. 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 So, you guys have any suggestions like what should we deal first? Yeah. 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 He, no, memory issues won't. Yeah, no, no. Memory of the space could no, but the thing is that you can push to a unbuffered channel only if there is a listening there, like somebody listen to it. So it essentially means that if you try to push multiple things to it, it won't. It is blocked there. It won't go through unless somebody is listening to it. So unbuffered channel, you can think about a pipe uh, that has a zero length capacity. So unless somebody is on the receiving end, you can't push things to them. But for a buffered channel, you can actually push multiple things to it, given that till the size of that till that channel is put. So yeah, yeah. So I'll just show you an example right here. Uh, okay, here. Mm, uh, so I will put some Go routines. I'll write a function uh, gr1 and I write another function uh, Go routine 2. So suppose these two are the functions that keeps on writing to a channel. So suppose it accepts a channel input chan of integer. It accepts a integer, and what it does is, so I write a in a for loop. I will try to push some values to uh, this. Like I say, okay, int I equal to 0, I less than 10, I plus plus, 10 I plus plus, and I put I to this. Similarly, so yeah, and here I say input and chan int. Okay, so what these functions are doing, it's trying to just push values to this input channel, and let's see whether it works, like whether I can infinitely push things to it or not. So I just say ch equal to make chan int. So this is an unbuffered channel because I haven't specified the size of it, so this is an unbuffered channel. So what I will do is I will say go one to this channel, go one to this channel. Okay, this is typo here. So if I do this now, first thing is that since there is no one to listen to this output. Like there is no one listening to this channel. This shouldn't even execute. Like what will happen? It should end in a deadlock because I am pushing to this channel, but nobody is listening to it. So yeah. First of all, we would. I'll just wait for this. Uh, I just put an infinite loop. So you can see that now uh, these things can't push like this. I can't push into this integer can't be pushed to this channel just because of that there is nobody listening to it, right? So what if I do uh, 29 ch and so, yeah you can see it was printing it. Eventually there was a deadlock here. That was essentially because I'll come to the deadlock point, but you can see only after if there is somebody to listen to a channel, only then I can push to a channel. As we saw earlier, I was trying to push something to it, but nothing was happening since nobody was listening to it. Okay. Uh, I think it was Madhu, right? Madhu, did you understand the concept? Yeah. So coming back to the deadlock thing. So this is something that you need to be aware of while using channels. So what happened was that I was pushing to these were the two go routines that were pushing to these channels. And what happened after this loop got ended, there is no one to push to this channel, as well as and for the go to same thing. Once this loop was ended, they are not pushing to it. And now what's happening is we are trying to receive some values from this channel, for which we know that nobody is trying to push to this channel. So at this point, nobody is trying to push to this channel, and we are trying to grab a value from it, and it is a deadlock. Now Go responds to deadlocks with a fatal error. Fatal error means it prints the error, throws the error, and it exits. So when you're writing this kind of code, make sure you are not going to run into deadlocks. And there are ways you can handle this kind of errors, but still when you're writing channels and when writing and reading from channels, just make sure you are not going to run into this issue. And so to make this, to avoid the issue of like if somebody is giving me what if this Go channel was giving me, okay, I'm done writing, now you can go ahead and do whatever you want. Those kind of, if it is giving me a way to do similar stuff, it would have been much easier. So what I would do is I would say I would make two channels. Channel goodbye goodbye 1 as main chat pool, and goodbye 2 make chat pool. And what I'm doing is I'm just passing this goodbye 1 by 1 as well as goodbye 2 to this, and I'm using a switch. No, sorry, not switch, select, my mistake. Select and case ch then we print line x, and case case goodbye one, case goodbye one, one second. We say cleanup equal to 2, say cleanup minus minus, and we say case goodbye 2, then we say we again do a cleanup minus minus, and instead of this what we do, if cleanup if cleanup is equal to 0, then we say return. So what will essentially happen is, what I have done is okay, I have to pass this channel exit channel bool channel bool, and once it's done, I say I'm just sending a value to this channel. Once I'm done with it, exit. So if I run this function now, yeah, you can see what was happening was I initialized two channels, boolean channels, and I send it to this go routines, and I was normally reading from the output channel from to which this go routines were here. This to this go routines were publishing to, and whenever I am receiving a cleanup, what essentially was doing was that from the goodbye channel, if I get something, I was essentially making sure that I cleaned up one function, and if the cleanup is 0, then there is no one to wait for. And there's something similar that Go provides, that's called wait groups. So there is a library function, instead of not like we were actually doing this kind of things like cleanup equal to 2 and cleanup minus minus. So there is something called wait groups. So wait groups is like something similar. What it does is we can actually do the, instead of this doing like this is a hacky mechanism that I created right now, but Go provides these things in a much better way. That's called wait groups. So that's way to implement this. Did everyone get this example? Okay, you are reading from a channel, but there is no one to push to the channel. Yeah, that was the reason for that deadlock. That's what you are referring, right, Manish? Yeah. So yeah, this is a way. So guys, you want to, guys want, I think we still have some time. You guys want to build something like with Go routines? Yeah, we can suggest something. We can try. Okay, cool. Okay, then I can do one thing. Let's try to implement a cache. So long time we used to do that. So it should be easy. And so I'm just doing a. We just make a small miniature version of Redis. Okay. Redis.go. We'll support a few functions, like we can put some string, we can get some string. Okay. And So we can make a like I can define as request a struct, and in this struct what I would say, I have a command. Basically command is string, and I can get a value, that is again a string. Command value, and instead of value I would just keep it as args arguments, and let's just take one argument. That's the just it's just get and set, so just we'll take just one argument, and we would return a value. So result as string. So what I'll do is I'll make a redis function. Func redis. What it needs is an input. It needs an input and output channel. So it would say in channel. So instead of the result out, I would say out. So basically this redis is an function that I am intending to be a Go routine. It takes an input channel, it's listened to the input request and gives some output accordingly. And to keep the caching, I would say I am keeping a map of string as key and value as string, and I'm starting an infinite loop where what I will be doing is I will just basically wait for some input request to come. So request equal to input is a string of request. Yep. Then what I'll do, if I'll do a switch request dot cmd. If it is a case of set, what I will do is cache of request dot args equal to it has to be array. We have to support like multiple values, so basically set key as value, and so that for that arg of 0 equal to cache request arg of 1. So basically if I am sending a set command, it will store the value in the cache. Case get, what I would do is I will return instead of return I would send out a value to the like if I get the value I would send it out to this channel. So I am hoping none of the time I would get an empty, like I won't get a request to get a value. Basically that's not, so I will just do one thing. Okay, I'm ignoring this, and cache of request dot r of 0 and what I'm doing is in this request there is an output channel. So what I'll do is into that output channel I would return this request itself. Result equal to what we are getting from this, and we send this request here. Yeah. So that's the redis function. And in here what we'll do is we'll initialize the Redis Redis cache. Then we will we'll just send a so yeah, for that you have to create a request channel ch equal to make request, and we initialize with this, and we make a request. I want to set a value, so rec set equal to request. I'm saying command equal to set, and args equal to string. It's a my val, and the value should be okay. I just put, I make it just symbol. I want to set name as Melvin, and the output as a channel. So output as an make request. Yeah. So what we'll do is we'll send this request to this channel. Set, and yeah, we just right away just test whether it works or not. After every iteration, after every request, we'll just print out the cache, what's there in the cache. Cache. So what if you try to run this? Go run redis.go. Oh, sorry. I have to wait for this redis thing. Instead of that, I'll just put a infinite loop. Yeah, so once I send some value, it got stored in that Redis key. And the way we did was we initialized a request and channel input channel with the request type, and with that we started the Redis, and we send this particular request to it, and this Redis waits for all the requests to come in. If a request comes in, then it checks what's the request has asked for. Based on that, it does this. And this is a nice way to keep a in-memory cache in it, and you won't have the issues of locking issues or unlocking issues, or basically it will be memory safety. So if I want to get a request, like if I make a I just copy this request. So I just need instead of get, I would do get. So yeah, just make sure. I'm just trying to get the value here. Oh, but I didn't print it right. Okay. So, and what I will do is var equal to request get dot out. So what we are essentially doing is we are waiting for this request get output channel that we created to give some values, and we will just print line val dot result. Yeah. So first time Melvin came when I put a set request, and next time Melvin came when I got the get request. Now I got the value from the get request, I just printed it. So this is a simple Redis kind of cache. And yeah, so writing this is not the ideal way to write this. This is a really bad way to write this code, but yeah, I think you get the idea, right? Like if I use a request in a similar manner, if I use something similar to this, it can be done a much better way. So if I can add something like delete and those kind of things, I can put all those logic inside this, and only this function has access to this cache memory, and no other function has access to it. So the chance of other variables coming and changing this variable. So what happens, sometimes we define some values in a global variable, and bunch of functions start manipulating it, and you can end up like today your code works, but tomorrow somebody also start using that variable and he's mutating it. Chances that your program run into logical errors is very high. But if you're using this kind of mechanisms where all the memory is residing inside a function, the chances of your code works the way it should be even after some time will be there. So does this example clicks to all, or is it easy enough? Okay. Yeah. Yeah. Sure. Hmm. Yeah. Yeah. It's fine. That is fine. So it's a ideally what should happen is like once I do this, I should like if I got out of this channel, ideally what I should do is I should actually put something similar like this, like close request get dot out. Basically, since I'm not using it anymore, I can actually free up the memory like this. So this is a nice way to do it, and there is one more better way. So now you can see that suppose this didn't go through, like for example here suppose if I don't do this thing, if I just if I comment this, what if I comment this? Okay, I have to comment this also. You can see that the second get request didn't get complete because I pushed a value into this cache, but what happens is it's trying to push some values, like it got the result, it is trying to push it to the output channel, but we are not trying to get value out of it. So essentially we are blocked here. No, the one bad request actually made our Redis cache, yeah, this Redis function to get blocked here. So there's a better way to do these kind of things. So this is something I usually do. What I do is I create a function called yeah, send values. What it actually does is it accepts an input channel and the value, that's a string, but it simply just puts the value like the value into this channel. Okay, now instead of doing this, what I will do is send values. Oh, sorry, this has to be request. And it is a go routine. So you know that for a go routine, if I make it a go routine, it won't block anything outside it, right? It would just go to the next line and schedule this go routine to be running in a way. So even if some operation or some bad code keep it waiting, or maybe it could be some operation, pending operation, or some web request, it could be keep waiting, but it wouldn't essentially keep my Redis blocked for other resources. Now you can see the moment I put a go routine here, what happened was it triggered a go routine, and this blocked, this input channel is still blocked, but since it is in go routine, execution continued to the next line, and this got printed here, but the other execution still stopped. So to verify that, I can do something. fmt line not executed. So basically that not executed didn't execute because this channel is still blocked here, since nobody is listening to that channel. We are not listening to this channel, so this channel is blocked, but Redis is not blocked. So if I do something very okay, I can do like this. Okay, I'll do two things. Request dot command. I just print request dot command here, as well as instead of writing this, I will do let it be like this. Then I will send one more thing, like to this channel. I would send request set, this time request set dot rx of 1 equal to days. So let's try it. So as of now, you can see that this get request, this input channels function is not executed, but when I said it wouldn't block the Redis, what I meant is, you can see the get thing didn't still not executed thing didn't happen, but it still didn't block the Redis thing from running. So this is a nice mechanism. If you add, instead of directly passing things around, instead of directly passing values to channel, if you put it inside a go routine like this, it can actually work. But beware to make sure that these things are actually properly handled, because at the end you could if there is a memory leak or something, you can actually end up running a bunch of spawning a bunch of go routines there instead of actually cleaning them. So that's something you need to do. So that's it. So do you have any doubts, any closing notes, anything? Okay, I think that comes to, so this is the references to the talks, like from where I prepared the slides and all, and also this is this is the link to that paper, CSP paper, that was initially written 1975, I think it's 78. So I'll share the link in the meetup page. There I'll provide the link to the slides. Also this recording of this tutorial, this workshop will be put in the YouTube. Also share the link to that also. That's from my side. So thanks guys for joining in, and guys have anything to say, or any doubt or anything, any feedback? So I have an give me a second. I have a link to that feedback. So I'm just sharing it here. So I have provided a link. Can you guys share the feedback here in this particular link? In the chat I have shared the link. So here just okay, sorry. Yeah, just share the feedback in this form. That's it. And thanks guys for joining in. It's been a great pleasure talking to you guys. Hope we can meet again in other workshops. Yeah, thanks. Yeah, sure.